Uh, Today we are going to study the subject power system 2, the subject code unit number 5, unsymmetrical fault analysis. The topic is line to ground fault. The lecture number 3. Myself, Dr. Tapre, HOD of the Electrical Engineering Department at SND College of Engineering, Java. The content of this topic, the syllabus is the symmetrical component, second, transformation matrix, sequence component, third, power in terms of symmetrical component, fourth, sequence impedance of the transmission line and zero sequence network of transformer. Fifth point is solution of the unbalanced by symmetrical component, line to ground, and double line to ground fault analysis of unloaded alternator and simple power system with and without fault impedance. And last, the numerical based on the symmetrical component and unsymmetrical component. The preamble of this topic is the unsymmetrical fault will have fully faulty parameters at random. They can be analyzed by using the symmetrical component. The standard type of the unsymmetrical fault considered for this analysis includes the following in order to their severity. First, line to ground fault or LG fault. Second is the line to line fault or LL fault. Third is the double line to ground fault or double LG fault. And last is the three phase to ground fault or three phase short circuit. Further, the neutral of the various equipment may be grounded or isolated. The fault can occur at general point F of the given system. The fault can be through a fault impedance, etc. Of the various type of fault, as above, the three-phase fault involving the ground is the most severe one. Here, the analysis is considered in the two stages under fault at the terminal of the conductor. Second, the fault at any point F of given electrical power system APS. Consider now the symmetrical component relation equations derived from the three sequence in network corresponding to a given unsymmetrical system as a function of sequence impedance and the positive sequence voltage source in the form of under VA0 which is equal to minus IA0 Z0. VA1 which is equal to EA minus IA1 into Z1, VA2 which is a minus IA2 Z2. These equations are referred as a sequence equation. In matrix form, the sequence equation can be considered as VA0, VA1, VA2 which is equal to 0 EA E0 minus Z0 0 0 0 Z1 0 0 0 Z2 and the column matrix IA0, IA1 and IA2 where VA0, VA1, VA2 it is the sequence component of the voltage, zero sequence component, positive sequence component and negative sequence component. Similarly, IA0, IA1 and IA2 is the zero sequence component, positive sequence component and negative sequence component of the current, and this is the Z matrix. This equation is used along with the equation that is considered under the fault derived to describe the fault under consideration to determine the sequence current IA1 and hence the fault current IF in terms of EA and the sequence impedance Z1, Z2 and Z0. Thus, during the unsymmetrical fault analysis of any given type of fault, two are considered for the solving them simultaneously to get the required fault parameter. First is the equation for the considering the under fault condition. Second, equation for sequence component or sequence equation. This is the figure which shows the LG fault on the conventional generator. Here, the three-phase winding of the generator is shown. So here, one winding, the LG fault is created. This is single line to ground fault on a conventional unloaded generator. Unloaded generator means where there no load is connected to this generator. A conventional generator is one that produces only the balance voltage. Let EA and EC be the internally generated voltage and Zn be the neutral impedance. The fault is assumed to be on the basis of on the phase A as shown in figure. Here the fault is considered on the phase A. Consider now the condition under the fault as under IB is equal to 0, IC equal to 0 and VA equal to 0. Means the phase O, when the fault is created on the phase A, that the voltage of the phase A becomes 0 and the current is also flowing in the current flowing in the phase B and phase C, it is also equal to 0. Okay, only the phase A current is flowing at fault point to the ground. Now consider the symmetrical component of the current IA with IB and IC equal to 0. It is given by the matrix IA0, IA1, IA2, which is equal to 1 by 3, 1, 1, 1, 1, A square, 1, A square, IA 0, 0. By solving this matrix, we can say that IA1, which is equal to IA2, which is equal to IA0, which is equal to IA by T, means the negative sequence, positive sequence and zero sequence current, it is equal and it is equal to the phase A current by 3. Further using the equation, above equation, we get VA0, VA1, VA2, which is equal to 0, VA0 minus Z0, 0, 0, 0, Z1, 0, 0, 0, Z2, IA1, IA2, IA1, IA1. Means the value we put in here same. So pre-multiply the above equation throughout the 1, 1, 1, we get the VA1 plus VA2 plus VA0 by pre-multiplying the matrix 1, 1, 1. And here we get the minus of IA1 Z0 plus EA minus IA1 Z1 minus IA2 Z. That is VA, means which is equal to VA1 plus VA2 plus VA0, which is equal to voltage of phase A, which is equal to EA minus IA1 into Z1 plus Z2 plus Z0, which is equal to 0. By solving this above equation, we can say that IA1 means the positive sequence current, which is equal to EA by Z1 plus Z2 plus Z0. Okay. So the figure 2, it is the connection of the sequence network or the LG fault on the phase A of a conventional generator. Means when the fault created at phase A of conventional generator can connect this all sequence network, means the positive sequence network, zero sequence, negative sequence network, and zero sequence network. This we see that all the connections are connected in series. Means the Z1, Z2, Z0, the value of Z0 it is equal to Z0, ZG0 plus 3 of Zn. So these are the all magnitude of the impedance are connected. The voltage of this sequence is VA1, VA2, and VA3, and the current which are flowing through this sequence is IA1, which is equal to IA by C. Same IA1 is equal to IA2, IA1 is equal to IA0. This is the final sequence network connection of line to ground fault if the fault is occur in phase A for the conventional generator. The above equation derived as above implies that the three sequence networks are connected in series to simulate the LG fault as shown in figure. Further, we have the following relation satisfied under the fault condition. First, IA1 it is equal to IA2, it is equal to IA0. Means the zero sequence current, positive sequence current, and negative sequence current all are equal, which is equal to the IA by 3. IA is the phase current, and which is equal to EA by Z1 plus Z2 plus Z0. And the fault current IF, it is equal to IA, which is equal to 3 times IA1, which is equal to 3 into EA divided by Z1 plus Z2 plus Z0. And the voltage VA1 means the positive sequence voltage, which is equal to EA minus IA1 by IA1 into Z1, which is equal to EA by EA into Z2 plus Z0 by Z1 plus Z2 plus Z0. VA2 which is equal to minus of EA into Z2 divided by Z1 plus Z2 plus Z. Similarly, VA0 which is equal to minus of EA into Z0 divided by Z1 plus Z2 plus Z. The fault phase voltage VA equal to 0 means the fault which are occur in the phase A, voltage of that phase becomes 0. Sound phase voltage VB means the healthy phases are VB and VC where the fault is not occur. The value of VB is equal to A2 into VA1 plus A into VA2 plus VA0. Similarly, VC which is equal to A into VA1 plus A0. Fault phase voltage VA into IA conjugate which is equal to 0. Sound phase power which is equal to VB into IB conjugate which is equal to 0 and VC into IC conjugate which is equal to 0. If Zn equal to 0, then Z0 equal to Zg0. And last, if Zn equal to infinite, then Z0 it is equal to infinite. That is the zero sequence network is open, so that then if means the fault current it is equal to IA is the phase current which is equal to. So thank you very much for the today's topic. Thank you very much.